This is Dylan Beresford. He's with NSS Labs. And without any further ado, give it away.
Thanks. Thank you. Thank you for being here. So again, I'm sorry that I couldn't get a hold of like a centrifuge from Iran and roll it in here or anything. These are actually PLC trainers, and it's basically a control box with some very basic data types. It's using Boolean with a signal state of either on or off. So what we're going to do during the demonstration, just to give you guys an idea, is we're going to reprogram the logic, the ladder logic on the PLC, and control different IOs. That way we can demonstrate how an attacker could control the PLC by capturing traffic packets going from the Step 7 engineering software to the PLC. It's very, very simple. The one attack vector that I just described is very simple, and we're going to cover that here shortly. But again, this is Siemens Simatic S7 PLC Exploitation, and I'm Dylan, and I'm glad to be here, and I thank you all for being here as well. I just want to go ahead and say thanks to a few people. NSS Labs for all the project funding. My best friend Brian Meixel for the engineering support. I couldn't have done it without you, man. My brother Ian for the lab setup in QA. Tim Otto for the hardware procurement. He got this stuff in a couple of weeks for me, which was really cool. I was worried I wasn't gonna have all the gear I needed. Del Peterson from Digital Bond. He's been kind of an inspiration to me, and he's helped me a great deal. Bob Radovanovsky from the SCADAsec mailing list. Everyone at INL, ICS Cert, I can't list their names, which kind of sucks, but for the help of the disclosure process. And then of course, plctrainer.net. That's where I got the PLCs and the trainers. Just real quick, PLCs, there's a lot of misconceptions about what they are. They're simply just computers used to automate mechanical devices. They're used in, of course, nuclear, oil and gas refineries, coal, water and waste treatment, transportation, aerospace, defense, commercial factories, among many other things. I have here with me an S7-300, and that's one of the most common PLCs in use today. It uses the Profinet IEEE 802.3 standard. It's very similar to Ethernet, but it's an industrial-grade Ethernet standard. And from an attacker's perspective, it's very easy to exploit because it's using ISO TSAP, which is a plain text protocol. Like many other programmable logic controllers, they use a plain text protocol. And the reason being is that these protocols were designed to be open so that developers could use the layered TSAP on top of the TCP to seamlessly create environments where they could write code to communicate across the network, because a lot of these devices, when they were designed, they weren't using Ethernet. This makes it really easy from an attacker perspective because we can capture those packets and we can look at them in plain text, and we can extract data such as server sessions. We can extract serial numbers of the PLCs, the model number of the PLC, as well as various different tag names that come from the data blocks in the PLC. We can even look at things inside of OB1, the organization block, which will allow us to look at the logic. So if an attacker wanted to, they could send out probes to the PLC, which would allow them to retrieve sensitive information from the PLC. Now again, keep in mind that these devices were designed to be used inside of a quote-unquote air-gap network, but as many of us know, air-gap networks aren't as common as one might think, based off of what we've seen historically with Stuxnet. Things can be brought in through removable media. When you see the exploit code today, I don't want you to think in terms of you would have to have physical access to the automation network. This code, the packets could easily be bundled inside of a worm and brought into an air-gap network, which could be used to attack control systems. And when you see the LEDs coming on and off, use your imagination. I mean, these could be gas pipelines, they could be valves, it could be a lot of different things. So again, TSAP was layered on top of TCP. Even if you add encryption to that, the encryption can still be attacked because it's layered on top of or in between the TSAP and the TCP. And we've seen that happen before with SSL. Another thing too is that it's not the protocol that's broken, so I don't want to send out the wrong message. It's the implementation of the protocol in PLCs. We need better access controls in PLCs, and that's something that I believe Siemens is working on right now. So Most S7 PLC firmware images are encrypted and hex encoded, and some, as I found, are using very simple rotating shift sequences to sort of obfuscate the strings in the firmware. The hard-coded password that many of you know about is actually BASIC. The username and password is basic. In German, it's BASISK. Very interesting. As we'll see later, going through the firmware with nothing more than a hex editor and 12 lines of Python, I was able to decode that password and get access to a command shell, which I'm going to try and cover that in the demonstration and show you as well. That command shell allowed me to dump memory from the NOR flash, the SD-RAM cached and uncached, as well as look at source code that had been left on the PLC. I also found that there was an open source web server that had been running on the PLC for some time as well. Simple HTTPD was running on the S7-300. So to my understanding, that backdoor is what I'm referring to it as. Siemens refers to it as something else, and I'll let Tomas explain that later. But the backdoor allows you to do much more than just check diagnostics on the PLC. I believe that it is definitely a backdoor into the PLC, and it allows you to execute arbitrary commands as well as intercept communications going to and from the PLC. You can also read data off of the micro memory card, the Siemens Simatic proprietary memory card that's installed in the PLC. So if one wanted to, let's say that you stored a password or you used a password to protect that S7-300, you could easily retrieve that password from the micro memory card where it's stored inside of the project file. And then, as you know, the authentication has been broken in the PLC. Unfortunately, I'm not going to demonstrate breaking the authentication, but I'll explain how that works later on in the demonstration until that's actually patched, because right now that's one of the only mitigation efforts in place to protect the PLCs so that plant owners and operators can prevent people from accessing it. So real quick, the device under test, it's very similar to what I do for my day job in the lab. I have two S7-1200s and two S7-300s. It's important to note that the S7-200, 300, 400, and 1200 are all affected by the replay attacks, as well as the weak password hashing algorithm that was used to protect the PLCs. The firmware versions are 2.2 for the S7-1200 and 2.3.4 for the S7-300. Now, keep in mind, Siemens said that the backdoor, the command shell, was removed in October of 2009. But for this particular model that I have here for the S7-300, the most updated recent firmware version available on the website contained the backdoor shell. So I'm not exactly sure if the developers weren't communicating with the CERT and they weren't aware that the shell was there. That's something that Tomas is going to cover, but I think it's really, really, really important that everyone knows that. This is sort of the internals of the PLC. That's, of course, the flash memory, and this is the inside of the PLC. There in the center here, you guys can see my cursor. That's the processor. They're manufactured in Japan, and some of the other parts are manufactured in China, in the People's Republic of China. I found that the network interface for the S7-1200s were manufactured at Siemens plant in Nanjing, which is pretty interesting, and I'm doing some research into that as well. These are the S7-300s. These are the big boys that Siemens, of course, claimed weren't affected by the replay attacks or the weak password hashing algorithm that was used. And what we found is that they were in fact affected, and I knew that in the beginning, even though I didn't have my hands on an S7-300, because it's using the same protocol essentially, and it's communicating with Step 7 just as the 1200s were. So I knew that if I captured traffic going to and from the S7-300, essentially I could extract the client portion from the TCP stream and build my own packets based off of that, put those into a library, port them into Metasploit, and then replay them back to the PLC and have it attack the PLC. So imagine this: if you can reprogram the PLC, change the ladder logic through Step 7, essentially you capture that, let's say in Wireshark, you dissect it, you create your own packets based off that, you replay it, and you own the PLC. That's one attack vector. I hope you guys can see that pretty well. This is Step 7 basic. That's a very basic network diagram where you have coils. They're either normally open or normally closed. This is the panels attached to the PLCs. Basically, the on-off switch will turn on all the LEDs Q0 through Q3, and the IO.3 will actually turn them off. So one has a signal state of 0, which is the on-off switch, until you turn it on, which changes it to a signal state of 1. whereas the signal state for the other has a signal state of 1, and then it goes to 0. So you can see here, this is just a basic diagram that I drew, because through this process, I look for vulnerabilities and write exploit code. I'm not a PLC programmer, so I had to sort of learn this on the fly in like 2 months. And it was actually fun. I had a lot of fun. In fact, I had more fun programming the PLCs than I did writing the exploit code, which was kind of painful. But as you can see here, switch 1 is normally close contact with a signal state of 0, data type bool. And this is sort of how it looks in step 7 as well. And then the off button. Essentially what we're going to do during the attack is we're going to change the signal states on all the different IOs on the board. So if we turn the on-off switch on, I know you guys probably already know this, but I just want to explain it anyways. The LEDs come on, press the red button, they go off. So as we know, the Siemens Simatic S7 300, 400, and 1200 rely on the Profinet IEEE 802.3 Ethernet standard for industrial grade connectivity. They say that, but you can use Ethernet cables. I made the mistake of buying Profinet cables. Regular Ethernet cables work just fine. They say that you need them because they work in a MES, a manufacturing execution system environment. I'm not necessarily convinced, but this is some data that I took from Profinet's website. They say today there are 3.5 million Profinet-enabled devices actively deployed. Out of those 3.5 million, we don't know exactly how many are Siemens Simatic, but what we do know is that they're probably PLCs or RTUs, and they're probably affected by the same vulnerabilities. Some of the private discussions I've had with ICS CERT, as well as other members in the control systems environment, the security, they said that this might affect a multitude of vendors, meaning it's not just Siemens. And I don't want to kind of blame Siemens for this, because what we're finding is other people, such as Del Peterson, the stuff that he does, is that these attacks can be executed against other manufacturers like GE or Rockwell, the ABB stuff. So by 2014, we'll probably have about 4 million to 4.5 million actively deployed across the world. I also checked DShield for scans of port 102 ISO TSAP. And what I've seen is that over the past 3 or 4 years, there have been quite a few scans showing up for people looking for these devices. And believe me when I say this, there are PLCs that are actively connected to the internet. People make mistakes all the time, and some of those mistakes, well, they end up causing damage and things get destroyed. I'm not here to freak anybody out, but I will tell you one thing. You look at the LEDs, you see them go on and off. If you attack a CPU on a PLC repeatedly, for 24 hours straight, you might cause pressure to build up inside of a pipe and cause an explosion. It goes back and it blows up an entire plant. So it's really time to sort of pull out that 800-pound gorilla out of the cage and take care of it now before things really get out of hand. What I've also found is that these capabilities no longer exist within a nation state, meaning that it's not just the spooks that have these capabilities. There are other people that can do this as well. There was a lot of misconceptions spread around about Stuxnet and how it would have taken millions of dollars in funding and a nation-state backing. I don't necessarily believe that is true. Not trying to discredit the theory, but saying that, you know, average guys sitting in their basements can pull this off. It is quite possible, and you should be concerned. Again, the S7 PLC listens on TCP port 102 for connections. There is no authentication mechanism, true authentication mechanism. There's nothing more than a server session that the Siemens Simatic Step 7 software generates. And the interesting thing about that session ID is that if I capture it from my S7 PLC, I can replay it back against any S7 PLC, meaning that I don't even need your session. I can generate my own. And even if you have a password, I can get around that as well. By capturing an authenticated packet, I can replay that packet back to the PLC. The PLC doesn't know where it's coming from. It doesn't know if it's legitimate or not. They can't tell the difference between Metasploit and Step 7. So the PLCs, both of them, the S7 300 and 1200, also accept remote commands over TSAP. We've also been able to attack the S7 1200 over ISO TSAP and actually cause it to shut down as well as the S7 300. Again, security was never factored into the equation. Packets are transmitted and sent in plain text. The protocol was intended to be open, and it uses a layering principle. Even if encryption is bridged in between the client and the server, as we've seen with some of Moxie's work, you could probably man in the middle of that as well and get past that. And another thing is the protocol hasn't been revised since the 80s, and I think it's time for people to look at the RFC and possibly add something to it related to security, because it's not mentioned anywhere in the RFC. So again, just the replay attack to go over it, some bullet points. We capture ISO TSAP traffic from the Siemens Step 7 containing CPU commands, ladder logic STL code, etc. We follow that TCP stream, walking you guys through recreating the attacks, dissect the client portion of the TCP stream, convert the packets into a Ruby-friendly format, insert into a baseline Metasploit auxiliary module, which I've included in my white paper so that you guys can take a look at that. And then we target the PLC. And just a quick demonstration of how that's done. Just to kind of show how easy it is to do this, how simple. This is a very simple stream here. We just extract where that red arrow is, that portion of the ISO TSAP conversation, and then we literally convert it from a C array into Ruby. And we replay it back, and we own the PLC. Siemens claimed that they had a mitigation strategy in place that would prevent replay attacks, and they did when I first spoke with them, when I disclosed this, but that was flawed, as I found. I kind of equate it to, if I capture traffic of you logging into your bank account, I shouldn't be able to replay that and get access to your bank account. That doesn't make any sense. So there needs to be better access controls in place. They also refer to this feature as their password protection for read-write access. That's not true either. They claim that if this feature is enabled, under no circumstances whatsoever can an attacker or unauthorized user access the read-write portion of the PLC memory, and of course that's not true. And we found that the 200, 300, 400, and 1200 are all affected by these attacks. Again, they also claim, well, here it is right here. I don't know if you guys can see this. I actually blew it up. You guys want to read that? That's the message that pops up in Step 7. Basically says, with full protection, it is not possible under any circumstances to download a program to the CPU. And I did it. It only took 45 minutes, actually. I got off the phone with the people at ICS CERT and Siemens. They told me about it. I'm like, that doesn't sound right, because if I capture that authentication packet and replay it back, I should be able to access the PLC. And sure enough, I was able to. So I believe that Siemens is now working on an upgraded version, which will be applied in Step 7 or 11, version 11, not 10. So again, this is what a session looks like there. You can see, if you guys, can you guys see that okay in red? Right in this area. That's a basic session right there, and that's pretty much all they're using for the authentication part. And again, this is kind of how it works. You capture that. You've got a hello probe packet to speak to the PLC. It comes back with some information saying I'm here. The authentication packet is sent, which is all of this, and the session again can be replayed. And if you have the right session, it'll grant you access. Here's the delta between two passwords. This is actually the encrypted password, but it isn't really encrypted. I was able to generate my own auth packets without Step 7 and replay them back to the PLCs and use the packets that I captured to generate a library of new packets containing, based off of plain text words, possible new passwords. So there's another attack vector there, is you could brute force your way in. Even if they do mitigate the issue with bypassing the replay attack with the authentication packet, it's possible that we could see people capturing hashes, Siemens hashes, and cracking those as well in the future, which is something that I'm working on with my friend right now. Again, they say memory protection, but there really isn't any, because we can actually dump from the NOR flash, the SDRAM, the EDRAM. Go back to that. I have another slide with that I'll come to in a minute. And some of the takeaways, again, it's also possible to generate our own library of packets based on a pre-existing packet capture and crack the password. Because Siemens does not enforce session expiration, we can simply use any server session ID we like against any S7 PLC, provided it's the same model. And then the memory protection takeaways, which we've covered. Additionally, we can disable the password protection. This is important too. If I want to, I can change the PLC password. So not only can I bypass the authentication mechanism, I can actually lock the plant owner or operator out of their PLC, which would really suck, because if you change the operational logic and you've got a process behind that PLC where there's pressure building up inside of a pipe and it's getting ready to explode, it's going to be really hard for them to even shut the CPU down without physically going over there and shutting it down. And some of these PLCs are deployed in the field. They might be 2 or 3 hours away from the plant. So if you change the password, essentially you're going to lock the operator out. And the security bit is what actually protects the PLC from being accessed without a password. It's literally a bit that gets flipped in memory, and it says, protect me or don't. Very, very simple stuff. And that's the only security feature that I know of that's integrated into the product at this point. So anyways, the process that we're going to go through is basically we're going to scrape device information from memory. We can change the results of the ladder logic on the PLC or manipulate the logic to report false data back to the operator, which is pretty cool. So if you have an HMI panel connected to something, you can actually send back incorrect data to trick the plant owner operator into thinking that everything's normal or functioning normal, at least from a screen, when in fact it's not. We can also edit the PLC device configuration. We could change the MAC address, the IP address, device name, time of day, again, lock the operator out of their own PLC. We can frag the PLC by triggering memory leaks and bugs that I've found. And when you think about denial of service, right, don't think of it in terms of IT security, because if you have to restart a web server, that's not really a big deal. You can go back and restart it, it comes back up. These are control systems, and if you attack one and it frags out, they have to physically go and find the device. Some of these devices are built into other devices that you can't even get access to. So that's another issue there as well. Chances are the plant owner or operator isn't going to be aware of what's going on. They're going to think it's a mechanical defect. They're going to replace the PLC with another vulnerable PLC. So if you have a worm propagating itself across the network, they're not going to know. They're not going to be able to detect that. And there's no logging information that's stored in the PLC that shows unauthorized attempts. So they're really not going to know what's going on. You're kind of stealth in a way. So again, what sets this aside from Stuxnet basically is that Stuxnet really pivoted off of the engineering workstation and hooked into a library to be able to communicate directly with the Simatic S7 PLC. I'm not exactly sure why they did that, because they really didn't need to go through all that trouble when they could have just simply gone straight to the PLC from the worm, right? And I think that was a big issue a lot of people brought up when Stuxnet came out. They were like, well, why would you need to pivot off an engineering workstation? They probably wanted something on that workstation, not necessarily wanted to pivot off of it. But what I found is that by simply capturing all the packets that you can from step 7 and generating your own library of packets, it makes it far more efficient to just replay those packets directly back to the PLC, and you don't leave any traces behind. Forensically, people can go back to the engineering workstation where you pivoted off of, and they can go back and find out what the payload was, where it came from, just as they did with Stuxnet. Whereas here, it's really stealth. I mean, I don't know of any forensics that are being performed right now on PLCs. I'm not aware of any. And of course, this could be wormed. We could pivot off of the Simatic S7 PLC, and we could even attack the engineer. And if we wanted to take it a step further, we could get to other PLCs. Other nodes on different subnets by hopping from one PLC that we've infected to other hosts within the network, other engineering workstations, and then to other PLCs, so we can propagate this. We can pretty much own everything on the automation network. And how do we do this? So there's a really cool feature in all of these Simatic controllers. We can actually pull the serial number off of the device. Siemens claims that this is a feature that they allow their customers to use so that they can identify the device. However, if you wanted to create a targeted attack, and let's say that you only wanted to attack, I don't know, centrifuges in Iran, right? You might have a database full of serial numbers, right? And you target based off of those serial numbers so that you can identify that PLC. That way you're not attacking friendlies, right? So this auxiliary module will be used to scan for not only PLCs, but vulnerable PLCs, because off to the right here, highlighted in green, it actually gives you the firmware version number. It gives you the model number. It'll tell us that this is an S7-1200, as well as a PLC name. And we're going to do a quick demonstration for the PLC memory read-write, where we're going to read device logic, connect to the PLC, create targeted attacks based off of that information, and read-write Boolean operations, and control what's in the data block. And I'll show you real quick. This is kind of what it looks like. This is actually binary data coming back from the PLC memory. This is coming from OB1 as well as data block 1. So we can see here a card reader writer. We can see Profinet interface. There's a lot of information that we can use, again, to create a targeted attack. We can even see the version that Siemens has compiled for the internal operating system. And here, this looks kind of crazy, but these are inside the data block, these are tag names: switch 1, switch 2, LED 1, LED 2, LED 3, so forth and so on. These are used for the programmer so that they can identify which bus belongs to which process. So if an attacker wanted to, they could read this binary data back and figure out exactly what's behind that PLC, because chances are the developers are going to name it centrifuge 1, centrifuge 2, centrifuge 3, yada, 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 or pipe 1, pipe 2, pipe 3. So we can use this data again to learn a lot about what's going on behind the controller if we're not there. And just to kind of enlarge a little bit, that way you guys can see what's coming back. This is the S7-300 memory dump auxiliary module. So Siemens, again, left a little backdoor in their product. And again, the password is basic. What we're able to do is use the tools that were left on there that will allow us to dump from, just real quick, the SD-RAM cached and uncached, the NOR flash, the EDRAM cached, scratchpad data with integer values, as well as scratchpad code, which shows us a lot about the PLC and how it was designed. You can actually see code paths to the source files on the PLC in a folder, a directory called source. So here's a dump of the memory here. Again, you can see information about the Profinet revision, PDEV stamp. A lot of this information might not be valuable to a typical attacker. What is valuable about this is that within this memory dump, there are passwords, there's information about what's going on with the PLC, the logic where it's stored, and we can essentially pull everything from the memory card on the PLC. So let's say that we can't get access to the engineering workstation, but we want those project files, we want the logic that's on the PLC, we can pull it off of that micro memory card. And we can do that through dumping through the NOR flash. Again, here's an actual source file here, cm_cla.c, and we can see some pointers there. And again, we can just pretty much dump through everything. This is where I found the hard-coded password at that offset. And again, I looked at it, and I could clearly see that this had passwords here and users. So I was like, So I just pretty much, through trial and error, I read the entire file into a stream, and then I started swapping the actual characters in the firmware. And what I came up with was this, which was pretty simple. I came up with the word basic. So it was scanning through the firmware, 12 lines of code, swapping every odd character, which allowed me to log into the telnet service as well as the HTTP service, dump memory, delete files, and execute commands on the PLC. This can also be used to spread malware, to propagate malware. You can actually put files onto the PLC. So here's what the inside of the command shell looks like here. I don't know if you guys can see that very well. Can everyone see that? Probably not. You guys see that okay? Yeah. So there's an interesting story here. When I was searching through the file system, I found, the reason I'm wearing this shirt is I found an Easter egg in there, and it had a bunch of dancing monkeys on an HTML page. And there was a German proverb in there. It's something along the lines of, all work and no play makes Jack a dull boy. And I was kind of surprised to find that, and I sent ICS an email, and they were pretty stressed out because I'd sent them like 20 emails in a day full of vuln information, and they're like, oh shit, and then I said something on Twitter, and they were like, not good, we have to put out an alert. I sent them the picture, and then Siemens corporate saw it, and they laughed, and they thought it was hilarious. So Tomas, actually, who's from Siemens here today, has some t-shirts printed up, and on the back it says pwned. So I give him major credit for actually wearing that here and being willing to come up. And before I go into the demonstrations of the attacks, I'd like for him to come up here and talk to you guys for a minute because in the beginning, the PR team was saying one thing, and they weren't talking to the engineering team, and things have seemed to change internally at Siemens. I give them a lot of credit for not trying to pull my talk, and I'd like to introduce everyone to Tomas.
All right. Thanks, Dylan, for letting me up here. I really appreciate that. So, how the hell did I get up here? Yeah, basically, I'm from the corporate CERT, so the emergency response team of Siemens. That said, I'm not authorized to speak entirely for the Siemens Corporation. That set aside, I really have to say that there are guys within Siemens taking care of the vulnerabilities that are in our products. me and luckily also a bunch of other guys. So at this point, you know, at some point we thought you really have to accept that there are vulnerabilities in your products and eventually even monkeys, you know?
Yes.
And I think really standing up and saying, okay, we have this type of stuff in our product, accepting this is the first step, you know, in order to be able to handle this professionally and in the right way, and also working out with the research community. We really appreciate the work with Dylan, which has been also responsibly in disclosing this over ICS cert to us and helping us to improve this. So anyway, if anybody up here or if anybody in the community would like to talk about vulnerabilities in Siemens products, feel free to approach me. I'm the guy with the German accent wearing the monkey t-shirt. Thank you.
Yeah, show in the back. Thanks, Tomas. Yeah, so again, there's quite a few Metasploit modules. At this time, ICS Cert is still working on an advisory and alerts. I've found quite a bit of vulnerabilities, even more so than what I can demonstrate today. But we have the command module, which is going to allow us basically to attack the CPU on the PLC. I won't go into all the details about why it's significant, but I will tell you this much. These capabilities have been used offensively before, and they have caused things to explode. When you see the LEDs, keep in mind that that could be pretty much anything attached to it, because we're not attacking the LEDs, we're attacking the controller. So we're going to go over the 1200 CPU command attack, the 300 CPU command attack, the memory dumping, as well as the CPU mem write, and the protection bypass, which I'm going to share some information on that, and then the DOS as well. So actually, I put another slide in here, so I want to make sure everyone gets to see this. Here are the monkeys that I found on the PLC, and yes, I thought that would make you guys laugh. I am definitely proud to be an American, and I don't know where Stuxnet came from, and no, I didn't have anything to do with Stuxnet, but I will say that I think all of us somewhat admire that capability. I don't want to go into all the myths about cyber war and all that stuff. I just want to say one thing: don't underestimate the power of the dark side. And there are a lot of people who are out there who are looking for ways to attack us, and we here are looking for ways to attack our adversaries. It's important to have this information out there so that we can make things safer for everyone, because control systems really do affect all of us. They affect the entire world. It's not just one nation. And at the end of the day, we all have to sit down at the same table and conduct business and trade. So yes, that's my way of saying fuck you to the president of Iran, Ahmadinejad. So yeah, Iran. Yeah, I said Iran. So real quick, let me explain the CPU cycles. So we have options in the Metasploit modules. We can set the cycle to 1, or we can set it to 10. The mode, you have 3 different modes. One will just turn it on, the other one will turn it off, and then we have one that will turn it on and off. When we're attacking the CPU, we can basically set the mode to 3 and cycles to 10, and eventually it will shut down the CPU and cause a hardware interrupt. So I'm going to go ahead and just show a quick demonstration of how that works. So if you guys want to come in and see this, I mean, I don't know if you guys can see the 1200s over here. Yep. And we can set the mode back to 2 and turn them back on. And set the mode to 3. Set cycles to, let's see, 6. Oh. This will actually frag the PLC, so the CPU can't handle start and stop commands that are being issued within a certain time frame due to certain constraints. So at some point, it will turn on, turn off, turn on, turn off, and then it actually will completely disable the PLC and shut it down. I don't know if you guys will be able to see it, but you'll see, if you come up close, you can see the LEDs in the front flashing. And that indicates that there's a internal firmware error. That's what Siemens reports. They just give you a little error code, but they don't tell you really what's going on. It takes a few minutes, so.
You mentioned it was Linux-based?
Yes, the 32-bit Linux, yeah. So I was expecting ARM or something, but no, yeah. While we're attacking those, go ahead and cool. And if you guys take a look at the S7-300s, I'm going to read from an invalid address, cause an interrupt, and shut it down. So you go down. Yeah, as you can see, it's flashing there, it's fragging. At this point, this would be considered a denial of service, but there's no way to bring the CPU back into a run state without actually power cycling the device. So we have to take it down, bring it back up, and the same with the S7-1200s as well. Even when they come back up, we have to issue another CPU start command. At this point, it'll be really hard for the plant owner or operator to figure out what exactly happened. So, excuse me, sorry. Whoops. Use the switch. All right, so that was a part of the demo, by the way. All right, so. 1200 CPU. So we'll set the mode back to 1. Or actually set mode to 2. Set cycles to 1. Exploit. Bring them back up. Cool. Those are back up, and then here. Let's see here. Auxiliary admin. DB1200 CPU. Right. Okay, so here we're going to reprogram the ladder logic on the S7-1200s. Oh, and another thing, this is multi-threaded, so if you want to attack PLCs at the same time, you can. I just want to do one thread per, that way everyone could get a chance to see it. So should be done here shortly. In the meantime. All right, I'm going to turn this off for a second. So, there we go. Here's SCADA. Set, offset. Let's do info actually. Grab something here. Offset to, we'll just start it. So this is dumping memory from the NOR flash from the CPU that's actually up. I need to bring, is that 300 still flashing? I may have fucked it up pretty bad. So let me restart it once more. Should come back up now. So, come back up? Cool, awesome. All right, so. So I'll actually read from an address with something valuable in it. There's a reference to the telnet service running on here. Actually, yeah. So here you can see quite a bit of useful information. You see some of the code, the source code, and if we set the length, get some more. So yeah, there's even some, it looks like, here we go, some HTML content. This is actually from the, yeah, there's a hot fix in here. We can see some other information in the HTML content from the command string for a tool that was put on the PLC for debugging purposes. So we can read pretty much everything from the PLCs. And here, for instance, we go to this address. These are just a few addresses that I found that show useful information that might be helpful. Didn't like that. Oh, forgot the A. Let's try this. Set, offset to this. Yeah. So here we can see a reference to the telnet server and the port and the HTTP server. And these weren't intended to run on the PLCs. Again, they were shipped according to Siemens by accident. So just to show you the command shell. So basic, right? And then we have a bunch of different files. So again, we can actually delete, we can remove everything off here. I don't want to do that right now because I might screw something up, but just to show you, actually go in here. And there we go. We can see here that we have access. Here's the Easter egg that I found. Yeah. In the tools, here's the memory dumping utility, and it's actually pretty useful. I can see where the developers would need to use something like this. But as far as, like I said, if an attacker were to worm this, they could read from an invalid address and shut off every PLC that they scan. It's pretty serious stuff, right? But they call it a feature. I think it's a backdoor. Yep. And there's even some references to, yeah, you can grab these files if I want to. I'll just remove something that's not really important. So I can make a directory like evil, or go into tools and remove trace, or actually, so I don't want to go in there. Sorry. I have 2 here. And that's actually on 24. So let's go to 24. And by the way, these are different versions of firmware on the S7-300s. So it's not just one firmware version that's affected, it's multiple versions. So here you can see our evil directory that we've created. No big deal, but we could store a payload inside there, put some malware in there to try and propagate across engineering workstations. Set of tools. We can see that we deleted trace init. If we want, we can delete the memory dump tool, since we don't need that. So we just refresh, and it's gone. So we pretty much have access to this hidden feature, this backdoor command shell. And I'll show you guys kind of what the exploit code looks like here. Very, very simple again. This is a stop CPU packet, and then there's a start CPU packet, and a very simple for loop, which will allow us, if we set it to 3, we can just attack the CPU basically by putting it in the start and stop mode. So there's not really much to developing the auxiliary modules. And again, I've created a template, so if you guys want to add stuff to the template, you can. This will be really useful for pen testers that are in the field and they want to search or scan for vulnerable devices. So that is the demo. That's it. And I thank everyone for being here. So.